In this video, I'm going to show you how to estimate a regression in Excel. And I have Excel open right now. I have the wage 2 dataset that is open right now. This is different from the dataset that you're using for your assignment, but it's very similar in theme. So it's some wage data that has been provided as part of the current population survey. In this data set, you have a number of variables that can affect your both monthly wage and your hourly wage, as well as the number of hours you work. You have the level of education in years. You have experience in years. You have tenure in years with the firm. Let me just zoom in so we can see these a little bit. You have age. You have whether or not the person is married, whether or not they're African American, whether or not they live in the South, whether or not they live in an urban area, the number of siblings, the birth order, so if you're firstborn, secondborn, etc., the education level of the mother, and the father's education level, as well as the log of their wage. So you have a number of different variables that describe sort of the experience of an individual person. So this is a data set where we can estimate a number of regression models that are associated with earnings. And we can put one variable, say tenure in years with the firm, to explain earnings, which is described by the monthly wage. We could have it just be solely described whether or not you're married, solely based on your experience, or we could include some combination of those things. And so the proposal is that maybe we should include some combination of those things. But when we're analyzing data in Excel, it's worth doing just a couple of small tasks to kind of help us out as we analyze the data. The first thing is we go to the View tab and we freeze the top row. Okay, so that has been frozen. You can see now there's a little line that distinguishes the top row from the second row. And so as I scroll through the data set, I'm just kind of scrolling around here. You can see that despite being in now row 430, I still know what the variables are. So this is something that if we use Excel to analyze our data, we can look at the columns to know what variables that we want to include. So let's first estimate a model where the monthly wage is just a function of the number of hours you work per week. So this is a very straightforward relationship. If you work more hours per week, you have a higher monthly wage. And we're in the 1970s. So monthly wages, you can see kind of going down column A, you're seeing a lot of wages that hang out in the, 1,300, 1,200, 900, 600. Earnings were less in the 70s than they are today. We would think all of these monthly wages in column A are not what we aspire to. However, in the 70s, things were different. So we have the monthly wage. We're just going to estimate it as a function of the hours worked. So we go to data analysis. Now, if you don't have a Mac, you can go to File, Options, Add-ins, Manage Add-ins, and add in the Data Analysis Tool Pack. If you have a Mac, click Tools, Excel Add-ins, and have that Analysis Tool Pack added in there. Okay, so I click Data. I click Data Analysis, and I scroll down to find Regression. I hit OK. Now what I'm going to do here is I'm going to delete all this stuff here. Okay, I'm going to delete the labels. And what I'm going to do instead is I'm just going to have my Y be the monthly wage. I'm going to scroll all the way to the top of my data set, take it, and then scroll all the way through down to the end of my data set, which is in somewhere in the 900s maybe. 936. Okay, so I clicked on A1. That was the label associated with the monthly wage. I have a colon, and then I go through to A936, which is the very last observation in my data set. Okay, so I'm trying to explain the monthly wage with the number of hours you work. The more hours, the higher the monthly wage. Of course, it doesn't account for anything like education, experience, type of job you have, etc. But more you work more, you earn more. That's the core estimate that we have here. So we go to column B, which is hours worked. Now I can type it in with an absolute reference to just be symmetric with what I did here in column A. I just type it in, or you can go back and click the data. Either way is okay. Okay, so just hit OK. You can click the residuals if you want to. We don't need them here. So we're actually not trying to generate 935 residuals here. Just hit OK. All right, the regression has been calculated here. Behold, there it is. Okay, we've got a bunch of information here. So first of all, it's worth considering what we did here. We estimated y equal alpha plus beta x, but the y is the monthly wage, and that's equal to alpha plus beta times the hours worked. Okay, so I have the monthly wage as a function of the hours worked. And so what Excel is producing is our best estimate of this relationship. So our monthly wage is the y. The alpha is the intercept. That's 981.315. You can see that right here. And the hours worked, this is actually negative. So already, even though I was describing the intuition for more hours worked, more higher monthly wage, that actually does not hold true in this data set because we haven't accounted for occupation, education level, experience, any of those types of things, and those are actually driving the monthly wage. So I think this regression right off the bat shows you the limitations of just having one variable attempt to explain why. Here's a variable we thought would explain it, but it actually doesn't do a very good job. Okay? So that is the estimate that we have there. This is the regression equation. And we're just going to highlight it here. A comment that I have is that we replace the symbols associated with the coefficients with actual numeric estimates. Actual numeric estimates. And those are located in column B. Okay. So this is the estimate. We estimated this equation, which is a little bit counterintuitive, but there's some other information that is included in the regression. Okay? So you can see column B produces the equation, and that is how we found it in class. You take the mean of x, you take the mean of y. X was the hours worked, y was the monthly wage. You take the standard deviations of each, you take the correlation coefficient between them, and here it actually seems like the correlation coefficient was negative because the sign of the slope is negative. And you can find the intercept and the slope as we did on exam 2. However, Excel produces more information than that. So Excel automatically tests the hypothesis that beta is equal to 0, i.e. x and y are not related. So our estimated relationship is that as you work one more hour, your monthly wage goes down by 53 cents, 53.2 cents. So that is the interpretation of beta. That is the sign and magnitude. The sign is negative. The magnitude is minus 0.532. Okay? So, from the coefficient estimated of the slope itself, we can get the sign and the magnitude associated with the estimated relationship. But Excel automatically tests the hypothesis that x and y are not related. So Excel makes a t-stat for us. the t-stat is equal to the slope beta hat minus 0 divided by the standard error of beta hat. And the standard error is comprised of the sum of squared residuals divided by n minus 2. That's take the square root. That's the standard deviation of the regression. And the sum of squared deviations, take the square root. So instead of producing the sum of squared residuals, it actually does produce the sum of squared residuals. You can see it up here. But instead of using that as part of the test statistic, it just produces the entire denominator of the test statistic in column C. So column C is the denominator of the test statistic. And the t-stat, we would take minus 0.532 divided by 1.832. And you can see over here that if I take minus 0.5, if I take the sample slope, take that sample slope divided by the standard error, which is in column C, I get the t-stat, which is located in column D. Okay. Those two things are the same thing. So column D produces the test statistic needed to test the hypothesis. Now, when I said Excel automatically tests the hypothesis, just producing a test statistic is not, in fact, a test of the hypothesis. We actually have to do a little bit more, but Excel produces a p-value for us. So the p-value is the probability that we would observe our data if the null were true. High p-values, less likely to reject the null. So if the p-value is less than 0.1, we reject at the 90% level. If it's less than 0.05, we reject at the 95% level. And if it's less than 0.01, we reject at the 99% level. And so just a comment, if you see e to the minus whatever, that's less than 0.1. It represents scientific notation. Okay, so here the p-value is greater than 0.1. Don't reject the null. Now we can also use Excel to make a prediction. So if we go over to column K or wherever you want, you can type in values, and in column L you can type in predictions. What I propose we do in order to make a prediction in Excel is take the regression equation that you see here, write it down. How would I make a prediction? Suppose we wanted to make a prediction for x equal 30. What should we do? What should I do? Well, ideally, you'd think, hey, man, you probably want to plug it into the line. Yes, I do want to plug it into the line. I plug it right in for 30, so I have minus 0.532 times 30, and then you add 981.315, and you get a prediction. Shouldn't Excel be able to do this for us? Yes. I type in 1 for the value of the intercept. I treat the intercept like a placeholder. I type in 30 for the value that I want to predict, x equal 30. Then I just multiply. I multiply the intercept times its value. And it shouldn't surprise us that 981.315 times 1 is 981.315. I multiply the slope times the value that I'm interested in, which is 30. I get minus 15.95. I add them up, I have a prediction. Now we can look at what's called the R-square. This is the percent of the variation in y that is explained by x, and almost no variation is explained. So, if we're looking at these data, there's a negative relationship between x and y that we estimated. It's not a statistically significant relationship because we don't reject the null at any level. And when you plug values for hours worked into the line, the monthly wage goes down, as you can see by the prediction we made over here. So this is one variable in the regression. One variable. The only variable we put in the regression is hours worked explaining the monthly wage. That may be insufficient, so I may want to have education and experience as well as the hours worked, which I already do not expect there to be a relationship between hours worked and monthly wage, but I might think that education and experience are related. So we go back to data analysis, regression. What I'm going to do is I'm going to keep hours worked, but I'm also going to include education and experience. So we're going to go back to the data. We're going to go all the way to the top of the data set. We're going to go here, keep hours worked in education. I'm going to scroll all the way through to the end, all the way through to the end. I have it. I hit OK. Cell's estimated regression for me. Here we are. Couple comments. The intercept was positive, now it's negative. The hours worked is still negative. The R-square went up. What did we do statistically? We estimated y hat is equal to b0, that's the intercept, plus b1 times x1 plus b2 times x2 plus b3 times x3. Okay, that's what we did. And b0, that's the intercept. b1 measures how a 1 unit change in variable x1 impacts y. b2 measures how a 1 unit change in variable x2 impacts y. b3, you can kind of tell the story here. It measures how a 1 unit change in variable x3 impacts y. And these are correlations, these are associations. We shouldn't necessarily think of x1 as causing y. Even if there is a statistically significant rate relationship, it's not necessarily the fact that there's causality. To just expand here, x1, hours worked. x2, education. x3, experience. Okay, so we have hours worked, education, and experience. So what we're estimating here is monthly wage equal B0 plus B1 times hours worked plus B2 times education in years plus B3 times experience. Now, that yields the equation that you see here. Monthly wage is equal to minus 190.88881, this is estimate, minus 1.995 times hours worked, plus 76.736 times education, plus 17.552 times experience. That is what we estimate here. So you can see that I took the numbers from column B, and I used those numbers. Go grab the color wheel here. Let's take this one here. Hit OK, and then do it again. I get the numbers in this equation from column B. And so now we're trying to explain the wage not just with hours worked, but also with education and experience. And the methodology that we use to find the mean of X, find the mean of Y, well, the problem here is that X is multidimensional, and the correlation coefficient between Y and X is really a matrix of correlations, so we have to use Excel instead to estimate this regression model. Now, Excel tests the hypothesis that null B1 equal to 0, alternative B1 not equal to 0, the null B2 equal to 0, alternative B2 not equal to 0, and B3, HO, B3 equal to 0, HA, B3 not equal to 0. So Excel tests all three. It tests a hypothesis for each of the X variables in our data set. So it's examining independently whether hours worked has a relationship with monthly wage, whether education has a relationship with monthly wage, and whether experience does. So the t-stat for beta 1, we take beta 1 minus 0 times, and this is beta 1 hat, minus, or divided by beta 1 standard error. And that's this thing, minus 1.995 divided by 1.712. And you can see that if you take this one divided by this one, that these two things are the same thing. Okay? You can do the same thing for beta 2. And we do the same thing for beta 3. So Excel produced 3 separate test statistics associated with 3 different hypothesis tests. And you can see that the last 2 hypothesis tests, we have really low p-values. So we would reject the null that there's no relationship between education and monthly wage. And we would also reject the null that there's no relationship between experience and monthly wage. These 2 are significant at the 0.01 level. You can see the p-values are really low. A comment that I have here is, even if you don't like looking at the p-values, you can always compare the t-stat to row n minus 2. Here, n minus k minus 1, k x variables. So here it would be row n minus 4. And if you do that, you're going to compare to, and the number of observations we have is 935. So you go to row 931. Clearly, the t-stat's bigger than all the values in either row 100 or row infinity. So you can reject the null for experience and education, but not for hours worked. Now, comment about these coefficients. We estimate that a 1 unit change in hours worked reduces monthly wages by $1.995. We estimate that a 1 unit change in education increases monthly wages by $76. We estimate that a 1 unit change in experience increases monthly wages by $17. So these are the signs and magnitudes of what we just found. But not with this color. So, comment, these are the signs and magnitudes. You get them right out of the coefficients. The test statistics test 3 separate hypotheses, one for each of the variables that you include in the model, and you have 3. We estimated this equation. We could make a prediction for it. So let's go make a prediction. I'm going to just kind of reduce the size of some of these so that we can actually put it all on one thing here. But let's say we wanted to make a prediction for college grad. That's 16 years of school, 10 years of experience, 40-hour work week. Okay, so we're plugging in 40 for hours work, 16 for education, and 10 for experience. We plug in 1 for the intercept, 40 for hours work, 16 for college grad, 10 for experience. So it's like I'm plugging in 1 for the intercept, 40 for hours worked, 16 for education, 10 for experience, and then we just multiply across. And I multiply across by just taking the coefficient times the value that I plug in for. You copy it down because you can, and you get all these predictions. You add them up. And we predict the monthly wage to be around $1,100 for this person in the 1970s. So when making a prediction, create a separate column for the values and then multiply the coefficients times the values, add it all up, you'll have a prediction. So just a comment that I have about Excel, you need to have consecutive columns in your regression. So I can't use column B, C, D, and F. I have to move F to BE. So that is just a comment about estimation in Excel. If I had the variable married, then the coefficient associated with married would be about the change from being not married, which is 0, to being married, which is a 1. So if you have these 0, 1 variables, think of it as the change of going from being in one category to being in another category. Excel estimates this equation for us. It tests hypotheses for it. We can use it to make predictions.